need to close something. 1 second. All right, so now I'd like to introduce our guest speaker, Patrick Giles, who works at the Yukon University Research Center with the Northern Energy Innovation Team. Patrick has a Bachelor of Science in Mathematics, a background which undoubtedly supported the work that we'll hear about today. Patrick's presentation on imputing large gaps of seasonal time series data with applications to electric loads will explain and demonstrate a method for imputing large gaps of missing data. While applied to electrical load data in his example, this method may be appropriate for other high frequency time series with seasonal behavior and large data gaps. And I'll turn the microphone over now. Thanks for joining us, Patrick.
Yeah, thank you, Sabrina, for the introduction. Just going to share my screen. Should be good. Let me just start the PowerPoint. Swap. Okay. So you should be able to see the main screen. Awesome. So yeah, as Sabrina says, my name's Patrick Giles, and I work with NEI at the Research Center at YukonU. And the webinar today is going to give an overview of a method that was developed to handle large gaps of missing data in electric load time series, but I'm also going to show how it can be applicable to other data sources that exhibits certain specific characteristics that you will find in electrical load data. So first off, I'm gonna talk about missing electrical load data and what that means in context of this method and the missing data problem. So electric load data is important for a variety of power engineering applications, forecasting future electricity demand, integrating renewable power systems, or sizing new power generation. Certain applications require high resolution data to create appropriate models or simulations. And data that is logged at a high resolution is more likely to have missing values. Missing data can arise from sensor malfunctions, power outages, glitches in data logging software. And if you're logging data more frequently, there's a higher likelihood that something will go wrong. So the nature of missing data in electrical load data sets can be characterized in two broad categories. We can have sporadic missing data. We can have gaps of missing data. Sporadic missing data is characterized where you have individual points or small groups of data are missing, and gaps are many successive observations in a row that are missing. So handling sporadic missing data isn't really that difficult usually. You can use local data around where you have your missing observations to impute or fill in the missing data. So just linear interpolation is quite a common technique to handle that. But when you have large gaps of missing data, this is not as simple because if your data exhibits periodic variation or seasonality, which you do see in load data, interpolation-based techniques will not capture this. So as an example, this is a snapshot of a data set for electric load for some community between the May 25th and July 2nd. And you see there's a large gap of missing data between June 4th and June 23rd. And you can see the seasonality or daily variation that I was talking about, where we have peaks of electric load demand and then we have troughs, and it's very constant from day to day. So applying a simple interpolation, linear interpolation to this data, there's, depending on your software, there's any number of out-of-box, functions that it give you. It just will attempt to capture the trend, but it doesn't give you anything else. And this is obviously not sufficient. And then out of other interpolation-based smoothing techniques, Kalman filters, that are more complicated than a simple linear interpolation also will not capture this without a lot of tweaking and messing about. And again, depending on your software or the functionality, you might not even be able to do it. So that's one aspect of this problem. Another aspect of handling missing data I want to talk about is single versus multiple imputation. So many imputation strategies, like just simple linear interpolation will focus on providing best estimates of missing data. So they only give you single values, only point estimates. And this approach will underestimate the variability of the true data because you only have one estimate, just single values. So single imputations carry no information about the certainty of the imputed data. You have your imputation, but you don't know how good it is, and there's no real information associated with it to inform that. So for some applications, it may be extremely useful to have some sort of bounds, upper lower bounds, to describe the range of values that are most likely to contain the true data. So a probabilistic estimate. So multiple imputation is a framework from which we can get probabilistic estimates of missing data instead of just single point estimates. And the idea behind multiple imputation is fairly simple at its core. It's just generate many complete data sets from one incomplete data set stochastically, pool all these data sets together, you get a single average or central tendency, and then you have corresponding uncertainty estimates about this. You have your probabilistic bounds. So this next section, I want to talk about the method that was developed to handle this. And again, this was developed for electric load data. So a lot of the points in the next few slides will be with respect to that. But as I will show later, you can extend it to other data sources. So for some, let's say, univariate load data set, call it X sub t, measured per minute, logged over a year, so that t is within this set 1 to 525, 600,000. That is just the number of minutes in a year. There is some gap of missing data. We can subset X sub t by the dominant seasonality for electric load data. In this case, that's daily, such that we get this matrix, X sub I of j, where I is defined in the set 1 to 1440, j is 1 to 365, and I of j are just the minute and day of the year, respectively. So there are 1440 minutes in a day. There's 365 days in a year. We can then do an additional subset to apply the method to weekend and weekday days separately. So as you might have noticed in the previous slide here, some load during some days is higher than others, and that corresponds to, for this community, during the weekdays, there's higher load than during the weekends. So if we can subset our data by weekend and weekday days, this will capture the difference in the characteristics we see for weekend load and weekday load. So each row of our matrix X can be treated as a new variable representing a minute across all days in a year. We can use a running median across all the rows of our matrix X, call it bold M sub I. By fitting across the matrix rows, the effect of the gap size is mitigated. So if you have a gap of 5 days in your data, which may be significant, by subsetting the data in this way, you only get 5 missing data points for across all the rows of this matrix X. Then we can reverse these subset operations that generate our matrix X, and we get this, again, a single univariate time series of the underlying trend, and we'll call it M of t. So applying this method to that data set I just showed you a minute ago, we get the cyan time series, and that is this trend component. Note how the periodic variation has been captured, as well as it captures the difference between weekend and weekdays. Weekends much lower, weekdays much higher. So the next part of this, we captured the deterministic component, the trend component, but now we want to model the random component, the stochastic component. By capturing the trend component, we can get the stochastic component. So let bold E sub I represent the residual data after accounting for the trend that you see in equation 3, where we just take every row of the matrix X, subtract from it this trend component that we just estimated, and we get our residual data vector. And all these vectors are with respect to minute I again. So for each of these vectors, E of I plus 1, they're going to be highly correlated. So in other words, this detrended load over the days of the year is going to be very similar from one minute to the next. This is a function of the high frequency of this data. Because it's measured every minute, you're not going to see much difference in these time series from like the first minute of a day to the second minute of the day. The load isn't going to change that much. Then we can model the correlation by reversing the subset of operations like we did earlier for the trend component on our residual data. So we have these vectors, E sub I, and then we get this single time series again, epsilon sub t, equivalent to some constant phi times epsilon sub t minus 1, so the immediate previous observation plus delta t. Then phi will control the correlation from 1 minute to the next. So if phi was 1, that would imply a perfect correlation. Then delta t is an error term. So equation 4 is just it's a simple autoregressive process. It's not a super complicated time series model. So to estimate the delta term, for equation 4, we want to estimate the components. To estimate the delta term, we can take first differences of our residual component. So the difference between every vector E of I minus E sub I plus 1. And then for the resulting time series, we will get a probability density function for each di. We try and estimate that. We can estimate the density functions through kernel density estimation, which is a non-parametric approach. What I mean by non-parametric is instead of just saying, okay, we're going to assume they're all normally distributed, we're going to say, no, we're not going to assume any family of probability distribution. We're not going to assume any specific one. We're just going to use a non-parametric approach to flexibly capture any differences that might be present. So for, let's say, the 5th minute of the day, the probabilistic characteristics of that may not be the same as the 500th minute of the day. So by using this non-parametric approach, it will be more flexible. So we've estimated the delta component. Next, to estimate this phi coefficient. There's a closed form formula for that. It's just equivalent to the square root of the variance of this epsilon time series less the variance of the delta component that we just estimated, all over, again, the variance of the epsilon time series that we had. So the stochastic component for these periods of missing data is generated with random draws from the density functions that we estimated plugged into the recursive formula that was shown in equation 4. So this is what allows us to get multiple imputations and not just point imputations. It's these random draws, these stochastic simulations from the probability distributions we've just estimated. So from this point on, I'm just going to refer to this method as seasonal subset missing imputation, or SSMI, just to keep things simple. So some results. Let's see how this method works on some test data. So the SSMI method is evaluated on 3 yearly complete load data sets for remote communities in the Canadian North. All were logged at a per minute frequency. We will generate 300 imputations or random draws to approximate the underlying data generating process. Missing data is artificially induced by removing gaps of data of size 2.5%, 5%, and 10% respectively. So we're going to look at how increasing the gap size will affect this imputation method. And then the imputed data is compared with the data we artificially removed to assess the efficacy of this method. To qualify our imputations, there are 5 different statistics we're going to use. And we're looking at 2 main categories: accuracy and quality. The first 3 statistics here, root mean squared error, mean absolute error, and similarity, all try and capture accuracy. So through different functional forms, they're trying to get how close the imputations are to the true data. But the point of multiple imputation is not necessarily to perfectly replicate missing data. The point is more to generate estimates that are extremely likely. So probabilistically likely estimates, not necessarily exact replication. Because in true missing data, you have no validation data to compare with. You don't know how true it will ever be. So that's kind of the point of multiple imputation. That's what it's getting at. So to assess this quality and not necessarily the accuracy, we have two more statistics: the coverage rate and the average width. The coverage rate is the proportion of confidence intervals estimated over the imputed data that contain the true data. So confidence or coverage rate assesses how plausible the imputations are rather than their accuracy. So if you have a nominal confidence level of, let's say, 95%, right, and you put those confidence intervals over your imputed data, and you look at the frequency of the imputations that fall within those confidence intervals, you want to get as close to the nominal level, in this case 95%, as possible. And the average width is just the average width of these confidence intervals that you're fitting for the coverage rate. So in an ideal world, your average width is going to be as small as possible while keeping the coverage rate reasonable. So you want to minimize the width of your confidence interval while keeping the proportion of imputed data that falls within the confidence intervals as close to the nominal level as possible. So these are some results in a table for what we did. The SSMI method, we're contrasting it with another approach for missing electrical load imputation that is pretty popular, pretty commonly used, where just the average of days about the missing gap are used to fill in where there is missing data. We're going to abbreviate this to NAD, or nearest average day. And yeah, we impute missing values with these averages. So where one method outperformed another in the table, the result is bolded. So I'm not going to go through the entire table because that would take a while, but just some highlights. Overall, the SSMI does outperform this nearest average day method across all the accuracy statistics: root mean squared error, mean average error, and similarity. You cannot compare them based on the quality statistics, the coverage rate and the average width, because nearest average day is just single imputation. There's no probabilistic component, so there's no way to compare on the other two statistics. Looking at the root mean squared error and mean average error for the SSMI method, they are stable as gap size increases for communities A and B, but for community C at 10% missing data, you can see a notable drop in the accuracy. And then in addition, for community C, our coverage rate value totally implodes. So we're looking at, for this nominal level of 95%, and at 10% missing data, only 81% of the confidence intervals contain the true data, which is really not good at all. So it's interesting to see why this one community is failing at the 10% level, where if you look at communities A, community B, at the 10% level, you still have coverage rates over 90%. You have 93.4% for community A, 93.2% for community B. So yeah, that is interesting why this one community is different. So I want to extend this method a little bit and not just look at electric load data. So yeah, it was developed and evaluated on electric load data, but there's no reason it can't be applied to other data that have large gaps of missing observations, but they need to have similar characteristics. And these three characteristics are seasonality. So this data should have periodic variation. Otherwise, there's no point in using this method. You could just use some interpolation-based technique, right? The point of this method is to capture periodic variation. It must have enough sample size at each seasonality level. So for example, a data set measured per month over 10 years is only going to have 10 observations for each seasonal component, that is each month. That is not enough data to fit any sort of probability density function with any sort of accuracy. So you're not going to get good density estimates. And then the third point is the overall variance of the data can't be too big. So the variance of the data is large. You can use variance reduction techniques to just make sure the data, the model converges. So like a logarithmic transformation, which we'll show later, any number of other variance reduction techniques. Yeah, just to make sure the model doesn't blow up. The SSMI method, yeah, we're going to apply it to 3 data sources that are given in table 1 here. We have sunspot data, so monthly average sunspot numbers from 1749 to 1983. We have this Southern Oscillation Index, which tracks monthly differences in air pressure between Tahiti and Darwin, which is, I think, in Australia, from 1950 to 1987. And then the flow data, which is monthly flow data for the Iowa River from 1958 to 2006. So all these data sets, you know, they don't have much in common. They're all very different from each other. But I chose these 3 just to show that it doesn't really matter, you know, what the data is describing. It just has to have these 3 characteristics and the method will work. So for the sunspot data, and this point here was where the missingness was induced. The cyan is the average of 10 realizations from the SSMI process. The black is the trend component, so the fixed, the non-random component. And then the transparent purple here, the really light purple, is the true data. So you can see that the SSMI method, it captured the periodic component, but it didn't really capture the spikes in the true data. But again, I want to emphasize the point of multiple imputation is not necessarily to replicate true data, it's just to generate estimates that are very likely. Moving on to the Southern Oscillation Index data, you can see compared to the sunspot data, it is not as noisy. Maybe not, it is as noisy, but it's not as, doesn't have a high frequency. It's not as much data points. But still, the SSMI method performed fairly adequately. It captured the trend. You see there's a downward trend here, and their imputations have a downward trend as well. And it captured the periodic component of the data too. So for the flow data, if we just look at the raw data, untransformed data, you can see there's a variability here from around 0 to, there's a spike here that gets close to 80,000. And maybe a more consistent upper limit of 40,000. So this will make this very large variance, and it will blow up our model. So we can't really use the SSMI method on the raw data. I tried, it didn't work. I got like, yeah, I got coefficients in the model that were shown earlier that just were ridiculous. So we need to transform the data. And we can just use a simple logarithmic transformation, and that will reduce the variance. So doing that, you can see instead of between 0 and typically 40,000, we have between 6 and 12, which is much nicer. This is where the missing data was induced. And again, the transform data, the SSMI method, it does fit, it's adequate for imputations for sure, and it converged fine with the smaller variance. So some conclusions. This SSMI method showed pretty encouraging preliminary results for the test data it was evaluated on. Provided, again, this is the electrical load data, satisfactory imputations for 2 of 3 community load data sets. And overall, it did outperform the simpler and commonly used nearest average day approach. It also showed applicability to other sources of data, which we just went over, increasing the scope of this method beyond just electrical load data. Some further investigation, we're going to be looking at ensuring SSMI is robust to a greater variety of data sets. So just what you saw, the underperformance of community C, we want to try and make our method robust to any quirks or features in the data that, for whatever reason, caused the underperformance at the 10% missing data level. It's also of interest to investigate the effect tweaking components of this SSMI method has on the quality of the imputed data. So tweaking how we maybe estimate the trend component. Instead of a running median, we could use a different process, or we could investigate how the smoothness level of that running median affects the quality of the imputed data. So if you used for running median, if you used a higher constant or higher number of data of which it is evaluated over, you're going to get a smoother running median. And that can affect the quality of the imputations maybe. You could also look at how changing the estimation of the stochastic component, instead of using kernel density estimation, or maybe different ways you can use kernel density estimation, because there's lots of different techniques within kernel density estimation. So in future work, SSMI will be refined and then evaluated against more complex imputation methods. So not just stuff like nearest average day. You can have imputation methods that attempt to do what this method is also doing. So compare and contrast against with those, as well as forecasts and backcasts from time series models that have been designed to handle high resolution seasonal data, but are not necessarily tailored to this imputation problem. Any future comparisons will continue to assess not only the accuracy of the imputed data, but again, the probabilistic characteristics through the multiple imputation framework. And that's the end of the presentation. So I'd like to thank Dr. Michael Ross for his support with this work over the past few months. It's been really appreciated. And I'd like to thank all of you for coming and listening to this talk, and as well all the people at Scope for setting this up.
Great, thanks so much, Patrick. That was excellent. Very interesting. Certainly a couple of formulas went over my head, but maybe if I spent more time with them. So I'd like to open it up for discussion. And I'm just going to look for hands raised and also monitor the chat for a minute. Mike Smith has asked whether you have this written up somewhere.
Yeah, so I think a copy was sent out in a Scope email earlier. It also was submitted to an IEEE conference recently. It hasn't been updated in the IEEE catalog yet, but it will. I can give you the name in the chat. Just let me find it.
I can also send a copy out to Michael after. Mike after. I was wondering about your presentation at the conference and whether there were any attendees who were interested in testing out the method on their own data sets.
Yes, well, not really. There weren't a lot of people at my presentation. It was just the other people who were presenting in that section. But the person who was chairing that session didn't have any specific interest, but he did say, this method would be applicable to a lot of different areas, especially with respect to big data and machine learning, AI kind of stuff, where they have large data sets that may not necessarily be perfect and have large amounts of missing data or data that's problematic and has to be treated as missing. So he did point that out, but nothing specific was asked, no.
It would be, I wonder also whether there might be some local, even within the Yukon government, maybe areas that are dealing with missing data that could explore whether this method might be helpful for them. But that's not something you can answer. That's just a thought I had. And then I guess I also wondered about Community C. I know I'm dominating the questions, but did you have any theories on why you saw the difference there, or is that just a mystery?
Honestly, no. Its load characteristics, if you just looked at the raw data, were not any different from Community A or B. It didn't have any noticeable differences. So I'm not sure why. It's still a bit of a mystery to me why that happened, but it did.
Thank you. Any other questions from the group? Quiet group today. Patrick has put the name of his paper in the chat, but again, I'm happy to send it out to anyone with Patrick's support for that, of course.
Yeah, absolutely.
All right, well, that was really great. Oh, here, O'Connor's got a comment. So if you see Devin O'Connor's comment, he's saying this may be useful for the continuous monitoring data at water resources.
Yeah, that's really
explore.
Cool. You know, yeah, I know lots of, whenever you deal with data, missing data, or data that's contaminated and has to be thrown out is a problem, which kind of motivated my interest in this, because it is not necessarily relegated to any specific area or field. So yeah, that's cool to hear.
Great. Thank you, Devin, for that comment. All right, well, I'll pause a moment just in case there are any last minute questions coming into the chat. Barring that, thank you again so much, Patrick. That was really interesting, and it's pretty cool to see new methods being developed locally that could be quite useful and have a really broad application both within Yukon and otherwise. So very exciting. Well, for me, it's very exciting. Thanks so much for everyone for joining. The next scope talk that we're looking at will be in February, unless anything comes up in the meantime, and that's going to be looking at the Wolf Creek Research Basin. Of course, folks are always welcome to suggest ideas for webinars or to volunteer to deliver one. I'd be happy to hear from anyone at osa@yukon.ca. And in the meantime, I hope everyone has a great afternoon. Thanks again, Patrick.
Yeah, thanks everyone. Cheers.